In this module, we're going to consider Chapter 13 on water resources. It's probably very appropriate that we start in our examination of different resources with water, because water is probably the most valuable resource to us. In fact, the United Nations has gone so far as to declare access to clean drinking water a basic human right. And while that might seem relatively straightforward and not controversial, it took the United Nations a long time to get there. And it's a difficult issue. It's an issue around which there's conflict in the United States and in other countries. One of the things that makes it problematic is because it's actually difficult in many locations to get access to clean drinking water. And increasingly, in many countries, we have the privatization of water as a resource, and thus it becomes a conflict that has both political and economic implications as well. When we look at the water cycle, we can look at the different processes involved in moving water from one location to another. And we're probably all familiar with these processes: evaporation, transportation, precipitation, surface runoff, and groundwater flow. Let's take a look at the next slide more fully. In this slide, you see the process of water that precipitates down to the earth is then divided into two forms. Either the water infiltrates or it begins to run off. And if it starts to run off, it's probably going to end up in a river or a lake or an ocean before too long. If the water infiltrates, it's going to become part of the groundwater flow, which will eventually work its way towards a river, lake, or ocean. But it's going to move much more slowly. So the path that precipitation takes, either as surface runoff or infiltration, will decide the fate of that portion of the water stream. Evaporation can occur from the land surface or from ocean, and one of the things that we always need to consider is that vegetation has the ability to take water from surface water or the groundwater and then return it back to the atmosphere. That's called transpiration. So we often link evaporation and the transpiration process of plants into the term evapotranspiration, and just combines that process of getting water back up to the atmosphere. For water, California sure does, but you can make a water budget on a regional, very local, or even a global basis, looking at the water, the total amount of water that falls in precipitation, how much water enters the groundwater system, how much enters the surface water system, where evaporation occurs and at what rates, and to be familiar with, to make a record of how much water is in each of these forms. That can be extremely valuable to a region like California, where there's limited quantities of water and they need to have enough water on hand in order to meet the needs of the population. Next, we'll look at water as a resource. One of the unusual things about water is that on Earth's surface it can be found sometimes as a liquid, sometimes as a solid, or sometimes as a gas. Usually, most substances are present in only one form on Earth's surface. In its liquid form, we know it as the water we drink, the rain that falls from the sky, or what we could swim in. In its solid form, it would be ice or snow or a glacier. And in its gaseous form, it would be water vapor that would be very much familiar with on a hot, humid day. The amount of time that water spends in each one of those phases, solid, liquid, or gas, will vary. It turns out that a water molecule entering the atmosphere in its gas form is probably going to spend the least amount of time in that form before it gets transformed back as rain or ice or snow and precipitates again. And once it precipitates, it's probably going to have a longer residence time than it did in its gas form. Probably one of the most difficult challenges of water is that 99% of water is unavailable or unsuitable for human use. It's either in oceans, in glaciers or polar ice caps, and while we can use water in oceans for some purposes, it's salt water and not useful for us for drinking water. So, another way that it can be unsuitable is that it might be polluted. So a lot of water resources available to us aren't useful because they're not suitable for drinking water needs. I'd like to spend a long time looking at table 13.1, looking at the world's water supply. And when you look at the categories shown here on the left, when we talk about water in oceans, it turns out that 90% of water on Earth's surface is in that form. And a water molecule that enters an ocean can be expected to stay in that form for thousands of years. So there's a very long residence time for a water molecule that enters the ocean. It's going to be in the ocean for thousands of years typically. Next, we'll look at the atmosphere. Water in the atmosphere makes up a small fraction of our total water supply. Once a water molecule enters the atmosphere, it will on average spend about 9 days in the atmosphere before it falls back down to Earth's surface as ice or rain. Surface waters in rivers and streams constitute a still smaller fraction of our total water supply. Water that enters a river or stream will typically only be in that form for a couple of weeks. The next form in which we find water is groundwater. Groundwater constitutes 0.31% of the total amount of water on Earth's surface. And if a water molecule enters the ground, it may spend hundreds to many thousands of years within the groundwater before it emerges as in a spring or empties out into the ocean or a lake. You might think that lakes constitute a significant amount of Earth's water supply. And when I grew up in the Great Lakes area, I sure did. But in fact, it's just a very small fraction, far less than 1%. Water that enters a lake would typically spend tens of years in that form before it'll either evaporate or empty out into the ocean. Lastly, we have ice caps and glaciers. This constitutes the 2.1% of the total amount of water on Earth's surface. So a pretty good chunk, second only to oceans. And if a water molecule enters the ice cap or glaciers, it can spend tens of thousands of years in that form before it might eventually melt and return to an ocean or evaporate. I'd like to point out that the data here in table 13.1 is prime stuff for quizzes and exam material. Very useful information here. So be sure to be very familiar with it. Stop for a quick quiz. If water is so abundant on Earth, why are water resources such a big concern? And here are your possible choices. Take a look and consider before I provide an answer. If you need to, you might want to pause here as you read these, because I'm going to reveal the answer in a moment. The answer to this is water resources are not necessarily where humans need them and when they need them. So water might be available as salt water in an ocean, but not available to us for drinking water supplies. Next, we'll consider surface runoff and sediment yield. Runoff affects erosion and transportation of materials. Soil or rock particles are typically dislodged by the impact of surface water in the form of raindrops or water moving across an erodible soil or rock. Ask yourself which can carry larger particles, a fast or a slow-moving stream. Turns out that the faster the water moves, the larger the particle it can carry, and the larger the quantity of eroded materials it can carry. So faster moving water is more likely to cause additional runoff. Associated with excessive runoff is erosion. And here's an example of an eroded field. Notice that the reduced vegetation may have played a contributing part in the creating this rill erosion, as what it's called, rill erosion. And these rills develop as a result of one rainstorm after another, causing erosion to accumulate in particular paths, and thus the rill erosion begins. When we look at precipitation, one thing we typically do is divide our watershed area into regions of interest. The region of interest will depend largely on what our question is. Am I looking for water supply for my well, or am I looking for enough water to supply all of California? That'll determine how big a drainage basin I want to take into consideration. So we can look at drainage basins over various scales. This is a depiction of two different adjacent water basins or drainage basins, and notice that the boundary between them is known as a drainage divide. Why that's true is because a water particle, if you had a water molecule that landed exactly on top of the drainage divide, it'd be a matter of chance that determines which one of the drainage basin it ends up in. But if you had a raindrop just to the left of that divide, then it's going to stay in the watershed to the left. Or if you have a raindrop just to the right of the divide, then that bit of water will stay in the basin to the right. This is a very local interpretation of the drainage basin, but we can also look at much larger scales. In the United States, the drainage basin for the Mississippi River system. Notice that it extends up into Pennsylvania and all the way up into Montana. So it's a very broad region that eventually drains into the Mississippi River. The drainage divide marks the edge of two adjacent water basins, and I explained that water particles that fall just to one side of it or the other are going to stay resident in that drainage basin. We might be most familiar with the continental divide that divides water in the United States that would eventually end up moving towards the Atlantic Ocean, as compared to the west of the continental divide. Water would strictly be flowing towards the Pacific Ocean. But we also have a Laurentian divide, where water on the boundary between the Mississippi River system and the St. Lawrence Seaway River system are right next to each other through Wisconsin and Minnesota and Illinois. So we can look at a number of different drainage divides that just determine the boundary of a drainage basin. A number of factors affect runoff and sediment yield. Some of these are geologic factors, such as what type of particles are at the surface. The next is topographic factors. You're going to have less erosion on a relatively flat terrain compared to a very steep hillside. Next, we have climatic factors that might affect the situation. If you have snowfall, you're less likely to have erosion from the same area compared to an equivalent amount of rainfall. So climatic factors matter. Vegetation factors matter. If an area is heavily vegetated, it's less likely to be subject to erosion, so the sediment yield will be reduced. Lastly, we have land use factors. There are a number of farming techniques or urbanization techniques that can cause damage or can avoid damage to the soils of an area and either promote runoff and increased erosion or reduce runoff and erosive effects. So think about this situation where you have an image of a hillside that's been subjected to a wildfire, and that's killed off a lot of the vegetation. After that fire damage, will runoff increase or decrease? And will erosion increase or decrease? Without the vegetation there, we'll actually have the raindrops hitting the hill slope with more intensity. We'll have less tendency for the soil to absorb water and infiltrate into the ground to feed the roots. And so that will increase, the fire damage will increase runoff and erosion. So both runoff and erosion are increased as a result of this type of damage. Let's consider another case. In this situation, we have hungry goats that have eaten off all the vegetation in a particular location. Will runoff increase or decrease? Will erosion increase or decrease? Just as we saw for the fire damage, this type of removal of the vegetation will cause runoff to increase and cause erosion to increase. So how we manage our land in terms of its use, helping the land recover from wildfires, can influence both runoff and erosion. Now we'll begin to consider groundwater. The source of groundwater is precipitation that infiltrates into the ground. To understand groundwater systems better, it's important to introduce a number of different terms. We'll start with those shown in red on this slide: vadose zone, zone of saturation, and water table. In this image, we see the groundwater zone where precipitation reaches the ground surface and then begins to infiltrate. When it first infiltrates the soil, it enters the vadose zone, where some of the pore space is filled up with air and some is filled up with water. The portion that contains water, that water will begin to seep lower, as shown by the arrows in the vadose zone. When the water reaches the zone of saturation, it enters the space where all the pore space are now occupied by water. There's no more air in the pore space, so it's fully saturated with water. It can't get any more in it. That boundary between the unsaturated zone and the zone of saturation is known as the water table. So the water table lies right between those two zones. So the vadose zone is sometimes known as the zone of unsaturated soil conditions. Of that situation where you see the vadose zone, which is sometimes called the zone of aeration or the zone of unsaturation, and below that the zone of saturation, and in between we have the water table. Now in some soils it's actually possible for some of the groundwater to move up into the pore space due to capillary pressures, and we would then have a bit of a capillary fringe where there's a excessive amount of water above the water table in this capillary fringe, but it's a small detail, and we're just going to not consider the capillary fringe, which would lie just above the water table. In an unconfined aquifer, we have a unsaturated zone directly above a saturated zone, and the water table defines the difference between them. But there are other types of aquifers and we'll consider those in future slides. Time to stop and see if you have picked up some of this information. Here's a possible quiz question. The vadose zone differs from the groundwater zone in what way? You might want to pause it here because I'm going to go reveal the answer. The zone is unsaturated while the groundwater zone is saturated. And that's our basic definition of the vadose zone. Next, we're going to look at these terms in red, and we have a bunch more terms to consider. We have an aquifer, an aquitard, and an aquiclude. I've already used the word aquifer, and what it refers to is a water-bearing unit or some sort of soil or rock layer that allows water to pass through relatively freely and from which we might need to pump water if we need to rely on groundwater as a source. But aquitard and aquiclude are soils of rock that either don't allow much water to pass through or slow it down. That's an aquitard. And then soil or rock layers that almost prevent any water from moving through are called aquicludes. So aquifer means lots of water can pass through. Aquitard is somewhere in the middle. Water is going to be very much slowed down. And aquiclude means almost no water gets through. So we have those endpoints. To look at some of the other terms, I need some images. This image allows us to consider many of the terms on the previous slide. We have hilly area, and we have valleys on the left and the right of the hills. And we have two kinds of streams. On the left, we have an influent stream, where groundwater from the stream or water from the stream is entering the groundwater system. And on the opposite side of the image, on the right, you'll see an effluent stream, where water from the aquifer is entering the stream. So the one on the left, the influent stream, the water in the stream feeds the groundwater system. And in the effluent stream, the water in the stream is fed by the groundwater in the aquifer. Other parts of the images shows us the zone of unsaturation lying above the aquifer. The boundary between them is the water table. Because this is higher in elevation here than on the left or the right, water will tend to want to flow from the area where it's mounded up here to lower elevations. As it begins to flow, you'll see that it enters one of two kinds of aquifers on the right here. You can see an unconfined aquifer, and an unconfined aquifer means simply that the top of the aquifer, and the top of the aquifer would be here, the top of the aquifer is the water table. It's the top of the zone of saturation. In the lower aquifer, we actually have a confined aquifer. How we define this is, if you look at the upper interface for the confined aquifer below, this portion shown in blue, you'll see that the top is the top of this confined aquifer is a confining layer. Now that confining layer is saturated, but it probably is composed of an aquiclude, which doesn't allow water to pass through at all, or nearly completely shuts off all water flow. So the difference between these again is the top of a confined layer is, the top of a confined aquifer is a confining layer. The top of an unconfined aquifer is the water table. Also shown on this image is what's called a perched water table, where water that infiltrates the ground here might want to again move down into the aquifer, but at this point its downward travel is stopped by a confining layer. So water will mound up, groundwater will mound up at such an interface, and in this case it actually has a location where in this hill slope there would be a spring emerge where the water from the groundwater from the perched water table would actually emerge in the hillside and flow down the slope. A spring. Notice that you can't follow the water in this river back up further up the hill. The water just emerges at this location. Probably the layers just below this point in the subsurface won't allow water to pass through, so it's easier for the water to move across the surface than it is for the water to continue to move down through the soil or rock below. That shows a mountainside on the left or a hillside on the left, which is an area where the groundwater is being recharged with additional precipitation, and that water table moves down into the zone of saturation in the aquifer here, shown in blue. And the aquifer moves, the water in the aquifer will sink downhill like water always will, and moves into the valley toward the right of this image. Now there's two kinds of aquifer here. The upper one, you'll see again the top of the upper aquifer is the water table, so that's an unconfined aquifer. The blue layer below that, the top of that aquifer is a confining layer, so that's a confined aquifer. And so one of the things that's shown in this image is a well has been drilled from the surface in the valley down to the lower aquifer, down to the confined aquifer. As a result, the water is under pressure in that aquifer, so it rises to the surface as a flowing artesian well. So you can see water flowing at the surface because the water is under pressure, pressure that is there because the recharge zone is at a much higher elevation. This concept is familiar to those who understand the concept of a water tower. In the water tower concept, a small municipality might have a water tank where water is stored at an elevation, and it's stored at an elevation so that you can have a second floor bathroom and still have water pressure when you want to take a shower on the second floor. So this same concept works in our groundwater system to create conditions that can lead to an artesian flowing artesian well. Here again, that's the process shown here, is that the flowing artesian well emerges as a result of this water under pressure. The water tank or the storage facility equivalent to the water tank is the hillside to the left where the groundwater recharge is occurring. This is another image of the same thing that's probably more realistic in terms of the conditions that might be present. You can see the hillside to the left again is an area where there's water precipitation entering the groundwater system. We have one particular aquifer, the one that's shown with the blue tinge or the blue shading, and in the upper left we have the area where the groundwater is being recharged from precipitation. If you drill down into the aquifer up in the hills, you'll see that the water is under enough pressure that it rises above the top of the aquifer, but it doesn't rise up to the surface and begin to flow out. So that's a non-flowing artesian well. Down in the valley, we see in this close-up that if we drill down into the aquifer at this location, the water is under enough pressure that it will emerge at the surface and begin to flow out. That's called a flowing artesian well. When we begin to study groundwater movement, there's a number of concepts that we need to consider. The first of these is the hydraulic gradient, which basically tells us the slope of the water table. If you have a steep slope, then the water is going to be moving quickly. If you have a relatively flat flat slope, then the water will be moving more slowly. You can think of this as the same under the same concept of your car driving down a hill. When you've got a steep slope to drive down, your car will tend to want to move quickly. If you have a relatively flat slope to drive down, then you'll be getting less of a boost in your velocity from the gradient there. So hydraulic gradient refers to the slope of the water table. Hydraulic conductivity describes the ability of a material to allow water to move through it. So the more easily water moves through a material, the higher the hydraulic conductivity. If it moves very slowly through a material, then it's going to be a material with a low hydraulic conductivity. Porosity is different. It describes the percentage of the void space that's available in soil or rock. And lastly, we get to Darcy's law, which is the law that governs how groundwater movement, and it describes the relationship between hydraulic gradient and hydraulic conductivity in describing groundwater flow. It turns out that the quantity of water that can move through material is proportional to both its hydraulic gradient and the hydraulic conductivity. So both of these concepts matter: how much of a slope you have driving flow, and how much hydraulic conductivity, how much water that material can pass through. Gradient is depicted in this image. You can see two observation wells. The one on the right has a head, or the elevation that the water rises to in the well, which is described as H2. And on the left, you have the head or height that the water rises to in that observation well, described as H1. Well, if we take H1 minus H2 and divide it by D, the distance between them, then we'll have the hydraulic gradient. If you see a big difference in the two heads, then you're going to have a lot more groundwater movement. If you see a very flat hydraulic gradient, then you won't have much water passing through that region. So that's how hydraulic gradient can affect groundwater movement. That we're going to look at is porosity, and we're going to look at how cementing, sorting, and fracturing can affect porosity. You'll see a sandstone on the top two sets and shale on the bottom. And let's take a look at how cementing, sorting, and fracturing can each affect porosity. Let's look first at cementation, the percentage of cement. In a close-up of these two images, we see that the non-cemented sand on the left is more porous than the cemented sand on the right. So the cement actually fills up some of the void space, and so there's less pore space available for water. Now we'll look at sorting. If you look at the grain sizes of the image on the left compared to the right, all the grains are approximately the same size on the left, which means you have a well-sorted sand. On the right, you have grain sizes that vary considerably. That's a poorly sorted sand. Notice that the well-sorted sand has a lot more pore space. The poorly sorted sand on the right is less porous because many of the small grains fit in between in the space left between the larger grains. Lastly, we'll look at fracturing. These two images show us a fractured shale on the left and an unfractured shale on the right. The fracturing directly increases the porosity of the shale, and so we have more places for water to be stored in the fractured shale, and we have less porous material on the right in the unfractured shale. 13.2, which is a table that's very important, another one of those that offers lots of opportunities for quiz and exam questions. This looks at how porosity and hydraulic conductivity of different selected earth materials vary, and it's extremely important to help you understand the information in this chapter and in some of the chapters that follow. It looks at some soils and rock, that is some unconsolidated and some rocky materials, and it looks at the hydraulic conductivity and the porosity of those. For example, clays have a very high porosity but an extremely low hydraulic conductivity. In fact, the low hydraulic conductivity of clay is one of the most important things to get out of this. Whereas if you look at materials like sand or gravel, or sand and gravel, then those have very high hydraulic conductivities, even though they have lower porosities generally than clay. So porosity doesn't tell us the whole story about how much water can pass through. The size of the particles matters as well. When we come to rock, it's similar in that, well, actually, it's a bit different. The hydraulic conductivity is very much the same. Sandstone has a hydraulic conductivity that's relatively similar to sand itself. Dense limestone or shale, it has a very low hydraulic conductivity, just like clay. The difference between shale and clay is just porosity. In fact, you can get a shale from a clay simply by compressing it. And while that compression will change the porosity from very high to very low, it doesn't do much to change the hydraulic conductivity. That stays very low. If you have an unfractured intact rock such as granite, then it's very likely to have an extremely low hydraulic conductivity and a very low porosity as well. If you fracture that rock significantly, then both of these can increase. What this table shows you is some important understanding of the endpoints, clays versus sands, sandstones versus shale. But what the table doesn't do is tell you what happens if you have mixtures, or if you have particles in between. For example, silt has a particle size between sand and clay. It similarly has a hydraulic conductivity that's somewhere between sand and clay. So, do make sure you get the information out of this table from your textbook. Quiz question on this topic. Which of the following would likely serve as an aquitard? The answer is silt. Remember that an aquitard has the property somewhere between an aquifer, which passes water easily, and an aquiclude, which won't let hardly any water pass at all. So an aquitard slows water down but doesn't stop it. And that would be the characteristic of a silt, which has properties between a sand and a clay. So silt is the right answer to this quiz question. The rate of groundwater flow is proportional to the answer is hydraulic gradient and hydraulic conductivity. A higher hydraulic gradient or a higher hydraulic conductivity will increase flow, so it's proportional to each of those. Now it happens to be proportional to those at about the same rate, and so that's easy too, but that's the correct answer to this quiz question. Next, we're going to look at groundwater supply, and it's important to look at groundwater in terms of its potential drinking water source for the United States. Groundwater is the primary drinking water for about half the U.S. population. That is an important fact for a number of reasons. It's going to be very important in next module when we look at the potential pollution of this resource, but it's also in terms of important in terms of making sure there's enough supply, enough quantity of water to serve the needs of a sometimes growing population. A huge amount of groundwater in the United States is available, but the cost of pumping and exploring reduces the total quantity available to us in many situations. So if we have a home somewhere in an isolated area where there isn't municipal well water supply available, the homeowner might need to hire someone to come in and drill a well. Well, getting someone to drive the rig out there to drill the well is going to be expensive, and then once you start pumping water from the well, you might get enough water to supply your needs at your domestic water needs, but it's possible that you won't, or that you'll have to drill such a deep well that it could become prohibitively expensive to build a home here. But this is a depiction of a well that's been drilled relatively shallow to collect enough water that hopefully will supply the needs of the homeowner. Uh, One of the things that you'll see here is that it's not just the pumping of the water here isn't going to have just an economic impact. You can see there's a depression near the center of the well that we call the cone of depression. So here we see the cone of depression around a pumping uh, domestic well. And this cone of depression is going to potentially be very small or might be relatively large. And it will certainly cause drawdown. If the drawdown is limited to just the property around the home, then there may not be much of a impact at all. But if the drawdown from a pumping well is so large that the cone of depression expands outside the homeowner's property, then you've begun to potentially impact your neighbors. So what are some of the impacts of groundwater withdrawal? Well, some potential problems with it include the if you have overlapping cones of depression. If your cone of depression combines with your neighbor's cone of depression, that might reduce the groundwater elevations down to the point that both of your wells run dry. So the two adjacent cones of depression can combine and make things much worse. And you'd have to go out and drill a deeper well. It can alter the direction of groundwater flow, which in some applications might be extremely problematic. For example, if you lived near salt water or other groundwater sources that would be causing a pollution of your domestic well supply. You might simply be extracting so much water that you've made it so that you can't have a domestic water supply anymore. That would be a very negative consequence of reducing the groundwater elevations. When we look at the issue of groundwater withdrawal and we find that we're using so much water that it can't be recharged by precipitation, we get to a condition known as groundwater mining. So groundwater mining occurs in dry areas where you have relatively large population. It also occurs where you may not have large population, but you have extensive groundwater use for agricultural or irrigation purposes. And there are some places in the United States where this is a severe problem. That's using more groundwater than it can be resupplied by precipitation. There are many areas in California where this is true, Central California in particular, southern Arizona, and very famously across a region that spans from Texas up into Nebraska, where there's extensive overuse of aquifers for irrigation purposes. One aquifer in particular is famous or infamous for its problems. Who's in really rough shape? those who depend on the Ogallala Aquifer. The Ogallala Aquifer stretches from South Dakota down into Texas through and into New Mexico. And there are locations where there's only been a very modest decline in the amount of water in the Ogallala Aquifer, and there are places where there's been severe reduction in the groundwater table. In the areas shown in the red, there are declines of over 15 meters, or about 50 feet of reduction in the height of the groundwater table. And that means a whole bunch of domestic well supplies have gone dry in this area, and new wells have had to be drilled. But all that's doing is further reducing the amount of water that's in this Ogallala Aquifer. So this is one that a large span of people depend on, that is very infamously or famously running short of meeting the needs of the population or the industries in this area. Here's another quiz question. Groundwater mining is accomplished by conditions where pumping exceeds recharge. So if your pumping from an aquifer exceeds the recharge to that aquifer, you'll have met the conditions associated with groundwater mining. There's an interaction between our surface water resources and our groundwater resources that is very important. In some areas, it's critically important. The water in surface water and groundwater is really considered part of the same resource. We often have surface waters infiltrating into groundwater, as the aquifer is typically fed by gravity in a recharge system, but we also have groundwater sometimes re-emerging as surface water in the form of springs. So this interaction is certainly worth studying and understanding. We have different kinds of streams depicted here. We have gaining or effluent streams and losing or influent streams. That is, in the first image in the top of this, in condition A, we have a gaining stream where the stream is becoming larger in size as it moves along the length of the river as a result of water from the groundwater being added to the stream. So this is a condition where water from the groundwater moves into the stream. In the next image, in B, we see conditions of a losing stream, where water from the stream is moving into the groundwater system. And as this happens, the river will become increasingly dry as it moves along its length. This could actually continue to the point shown in the C condition, where you don't actually have connection between the groundwater system directly, except through the zone of aeration. So water enters the pore space of the zone of aeration and then sinks by gravity down to become part of the groundwater resource. This process can actually progress to the point where the river dries up as it continues to move down its length. Areas such as the Pecos River in New Mexico moving into Texas is known to dry up in certain locations. Curiously, it also re-emerges later as the Pecos River moves over relatively porous formations. More about the surface and groundwater interaction. Again, an effluent stream tends to flow all year round, is perennial, and it is typically, it's characteristically fed by the groundwater during dry weather. Influent streams, on the other hand, are above the water table, and they flow in response to precipitation, and they tend to form recharge mounds. Look at the interaction of surface and groundwater in areas where the bedrock can be dissolved by water. That leads to karst topography. When we have a soluble rock, such as limestone, we can have extensive connection between surface water and groundwater, where there's an easy connection, and this can be significantly problematic. We can have conditions where there are features such as sinkholes and caves and disappearing streams or a lack of surface streams, that the streams have all moved underground. This is actually what happens along the Pecos River that I mentioned before in New Mexico. You can come to places where all the water from the stream just simply disappears into the ground, and it looks like a little pool as water disappears and the river stops. And if you move a few miles downstream, you can find the place where the river comes back up to the surface near Carlsbad, New Mexico. So that's a really unusual feature, but it can also be really problematic in terms of pollution. If you have pollution at one location on the surface, that can quickly lead to contamination everywhere in the subsurface, and in other surface locations. We'll talk more about that in our next chapter, but let's take a look at some areas, some of these features of karst topography. Here's a number of lakes in a karst topography region, and one of the important things to understand about these separate lakes is that they're all probably connected. If you were to see one dry up, you would see that all the other lakes would be drying up at about the same rate. If one of these is polluted, they all tend to get polluted. So that can be problematic. Here's an example of a sinkhole, and it's a sinkhole that is subsequently filled up with water. We have significant problems. You sure would not have wanted to have ever built on the area that's going to be subjected to sinkholes, and if you did, you might very well lose your house. In Florida, there are a number of homes that every year it seems that there are sinkholes develop underneath newer subdivisions, and the problem of sinkholes can be devastating for those families, and even fatal in some cases. Here we have an area of karst topography underlain by essentially a line of sinkholes, where there must be a subsurface cave system extensive enough to promote the dissolution or dissolving of the limestone that leads to depression or sinkhole in a line above that cave system. Well, there's a lot of negatives associated with caves. But we also can have some really interesting cave features, as the flow stones or stalactites or stalagmites that develop in a cave system can be viewed as a dramatic scene and be the source of tourism industry. And for Mammoth Caves in Kentucky or Carlsbad Cavern in New Mexico, that's certainly true. A stalactite hanging from the ceiling, if it eventually grows to the point that it touches a stalagmite on the floor, would be called a column. If you've never been inside a cave system with these types of features, I'd encourage you to try it. It can make for a really interesting tour. Winter Park, Florida, we have this relatively infamous sinkhole that developed in recent years to consume several homes that had been in the area. And it's not just the homes, it has eaten into the roadways in this area and threatens to progress larger. These karst features can cause significant environmental problems, particularly if there's any water pollution source that one person contaminating the surface or subsurface anywhere in a karst region can quickly cause a regional problem. We could also have collapse of sinkholes that lead to problems in an area. And we tend to have these problems develop associated with groundwater mining. And if you read in your textbook, you'll find one of the case histories that focuses on the Edwards Aquifer in Texas, where this is particularly problematic. Question for you. You might want to pause so that you can select an answer here. What is karst topography? Why is karst topography a concern for groundwater quality? Because waste disposal in karst areas can easily infiltrate into the subsurface or into the ground. Next, we'll look at desalinization of seawater. As we saw at the beginning of this lecture, there's massive amounts of water available to us in the oceans on Earth's surface, but the problem is we can't use the ocean water for drinking water or for many other purposes because of the salt that is contained in that water. Desalinization, or desalting the waters, is very expensive, and that expense usually prevents the use of this method, except when traditional sources of water are not available. Desalinization is also linked to energy costs in terms of when energy costs are relatively high, then this is a method that we don't want to use or can't afford to use. We have some pilot programs. For example, in Tampa Bay, there's a seawater desalinization plant that has been in operation for many years. There are some locations around the globe where desalinization of seawater presents a very attractive choice. There are places in the Middle East that don't have significant groundwater resources available, but do have relatively low energy costs due to oil and gas production, where desalinization of seawater is relatively common now. Water use. We classify water use in a number of ways. We might have off-stream and in-stream uses, and we might have consumptive versus non-consumptive uses. What is off-stream water use? It's when water is removed or diverted from its source. Examples would be use of water for irrigation, for use of water in industry, or to supply to create a public drinking water supply. Those tend to be consumptive. This would be a type of off-stream use where the water doesn't return immediately. Examples would include water that goes towards crops or consumed by animals or humans. In-stream water use would be where the water is not withdrawn from its source, where water is used, but it's used where it was located. So hydroelectric power supply, wildlife habitats, recreational use of water, such as in river water used by boats, would all be examples of in-stream water use where it's not consumptive and the water stays in its original resource. To examine the conflicting needs for water, let's look at one location where water in a river meets a number of different in-stream uses. We might find that the navigation, for example, the ability for boats to be able to pass through the water might be relatively consistent. You just need a certain elevation of water. Fish and wildlife might have water needs that change from one season to another. There might be relatively little need for water in the river during the winter, but much more need for water for various wildlife in spring and summer. For hydroelectric, to meet hydroelectric needs to generate power, we might have relatively high need for water during cold seasons and less of a need during spring, and probably an increasing amount of a need for power in the summer for air conditioning. And lastly, we have recreational needs that would tend to be very low in winter and very high in summer. Here's a quiz question. What kind of water use does not divert or remove water from its source? That's what we call in-stream water use. If we look globally at water use, we see that about 70% of water goes towards agricultural purposes, about 20% towards industry, and only about 10% goes towards urban or rural domestic water supply. Water use, we have an overwithdrawal or mining of groundwater, and overuse of surface water is common. So we can sometimes dry up surface water sources and then begin to tap into groundwater sources at a rate greater than what then can be recharged. We have higher concentrations of pollutants in urban areas that can threaten the local water supply. There's a case history in your text that looks at the conditions on Long Island where this is very true, where waste disposal in Long Island has caused contamination of their very important groundwater resources. And there are naturally problems associated with importing water from other areas. And you see an image of an aqueduct in California where water from northern California mountains are allowed to flow through aqueducts to meet the drinking water and agricultural irrigation needs of Southern California. So aqueducts are one way, but it's not a very efficient way of moving water from one area to another. Next, we'll look at Table 13.3, which shows some trends in estimated water use in the U.S. from 1950 to 2005. And the important columns here are probably the last two on the right. We see the percent change from 2000 to 2005 to see what the trends are during that period. But when you look at these trends, make sure you also look at how much water is used within that category. So the first 2/3 of the table look at water withdrawal for different purposes, and then the bottom portion of the table looks at sources of water, how much we get from the groundwater and how much we get from surface water, both fresh and salt water or saline. If we look at the data as a whole from this 55-year period, we see that surface water use is far greater than groundwater use. And we also see that the rate of water use has decreased and leveled off since about 1980, even though our population has continued to increase. This suggests that there's a better understanding about the need to protect this resource in the public, and it indicates the use of new technologies and an increase in the use of reclaimed wastewater. Graphically, we'll look at that in this trend in the next slide. So even though we see the black line showing a gradual increase in population since about 1980, our water use has pretty much leveled off for both surface and groundwater. In terms of a summary of water supply and water supply use during this 55-year period, this figure might be easier to interpret than the table we looked at last. If we looked at various needs that are met by water use, while we see the total withdrawal of water has leveled off since around 1980, not all of the various industry uses or public supply uses have leveled off. Some have actually experienced decrease during that period, and others have continued to increase. This has brought a growing awareness of the need for water conservation methods. These methods include regulating irrigation and reducing evaporation, because that can reduce the water withdrawals for agriculture by using lined and covered canals and using night irrigation, for example, because if you irrigate at night, there's less evaporation as the water is supplied to the surface at the crops. Other methods include the development of new, more efficient technologies in power plants and other industries, and considering virtual water budgets on a global scale to create an increased awareness of the virtual water import, export, and local water demands. What can you do? Such things as to conserve water. You can take shorter showers, shut off water while brushing your teeth, running full loads of dishes and laundry only, not half loads or small loads, check for leaky faucets and have them fixed, and water plants only when necessary, water the lawn only when necessary, and watering at night or during periods when it isn't during the heat of the day. In areas that are subjected to significant drought or water shortages, these kinds of methods can become mandatory. For example, I recall when there was a water shortage affecting New South Wales and Australia, the people of Sydney were not allowed to take showers longer than, I can't remember how many minutes, but I think it was like 2. And you'd think that that wouldn't have gone over very well, but they actually had pretty good compliance from the population. Other components of water management is that water supply problems are particularly common in arid and heavily populated areas. Southern California is one of the places where this is true. But with the way water constraints work in California, it tends to be that all of California is constrained when there's a water shortage. Go ahead and look at the section called "A Closer Look: The Management of the Colorado River" in your textbook. It focuses on that particular location, and I'll let your textbook address that. Water is now treated as a commodity, and it's not necessarily it's a commodity that a lot of people take for granted. The residents of Flint, Michigan, in 2015-16 certainly learned a lesson on how not giving enough regard to the need to address water safety can become a problem. As for how we treat water as a commodity on a local, regional, national, and global scale, we sometimes have water treated as such a commodity that it's hard for us to recognize the need for drinking water to be a human right, and also for us and for those looking to make a profit off of supplying water, to have those needs met in a balanced way is a challenge. It's led to war in some countries, well, riots at least. Luna Leopold proposed a philosophy for water management that involves planning for natural excesses and deficiencies through the strategic use of surface water more in wet years and groundwater more in dry years, by considering additional reuse and recycling of water during emergencies. So the textbook addresses this philosophy fairly well. Here's a quiz question. The water management philosophy put forth by Luna Leopold focuses on what natural variability in water resources? You may want to pause for a minute. The answer is the natural variability in water resources. Recognize that we should draw on different resources during different years depending on the available water supply. Next, we'll look at water and ecosystems. Ecosystems change in response to climate, nutrient inputs, soils, and hydrology, and they change from one location to another, but they also change from time to time, depending on how these available resources cycle. We've recognized that wetlands, as an ecosystem, are worth protecting for the wildlife and for us, as we are often dependent on them. I'll give you an example of where wetlands are useful for our protection. Katrina 2005 hit New Orleans harder than might have happened had we not had so much wetland loss off the coastal Louisiana. So there's an example where had the wetlands been as vital as they had been decades ago, there might have been a reduced impact from when Katrina hit. Human use of water tends to increase the degradation of natural ecosystems. For example, when we create dams and reservoirs and canals to increase our available surface water resources. But these are not without environmental consequences, and dams create consequences at the dam location and upstream in lands that are flooded out, and downstream in lands that are deprived of water. And the ecosystems that are associated with wetlands, we're talking about swamps and marshes and bogs that are sometimes freshwater in some locations, like up in North Dakota and northern Minnesota. There's plenty of wetlands, but we also have saltwater marshes, for example, off coastal Louisiana. Wetlands are identified by the hydrology and the vegetation and the soil type present in those locations, and they have important environmental features in terms of what kind of wildlife they sustain, but also in terms of how they make other climatic variations or weather conditions affect the region. About half of all the wetlands in the United States, that is 90% of freshwater wetlands, have been destroyed in the last 200 years. So here your textbook has another section for you to read that will be useful, and it's a closer look at wetlands. Here's another quiz question. What are areas that are either inundated by water, in which the ground is saturated to shallow depths at least for a few days in most years? That's our definition of wetlands. Global water shortage. We do have isolated shortages of water that may be viewed as an indication of global shortage issue that's coming. We have depleted water resources that include overdrawn aquifers and dried lake like the Aral Sea, and troubled streams that are no longer reaching the sea. We often have polluted water resources due to development and increased and poor disposal of wastes. Our demands for water resources will increase dramatically as the population moves from 6 billion to 8 or 9 billion in the next 50 years. So, while there may not yet be a global water shortage, the chances of it coming in future decades is increasing. And it was a famous American, Benjamin Franklin, who said, "When the well is dry, we know the worth of water." And make sure you look at where your drinking water comes from. That's a very useful thing to know. And know what resources you're dependent on. You may be surprised, either for good or bad, but it's a useful thing for you to know.